Hi, in this video we're going to talk about solutions, concentrations, and molarity. So let's start off by talking about what a solution actually is. So basically, it is a homogeneous mixture of two or more pure substances. And by homogeneous, I mean that everything is more or less evenly distributed throughout the solution. So when we talk about solutions, we talk about two types of substances. We talk about the solvent, which is whatever the major component of a solution is, and we talk about solutes, which are basically any substances you have dissolved in the solvent. For purposes of this video, we're going to talk about the solvent as being a liquid and solutes being some sort of solid that gets dissolved. But that is not the only sort of solution there is. You can have gases dissolved in liquids. You can have liquids dissolved in liquids. You can have gases dissolved in gases. Heck, you could even have solids dissolved in solids if you want to talk about minerals and solid solutions. The reason that we talk so much about what we call aqueous solutions is that chemical reactions need movement. So if you have a bunch of solids that need to react with each other, how are they going to do that? In order to react, molecules need to basically come right up next to each other. And that doesn't happen very easily if they can't move around. So if you think about the process of photosynthesis, you need 6 carbon dioxides, and those are gas, and gases move a lot, so that actually ends up working out well. You need 6 water molecules. Water moves very well, and because they can move so easily, they can come together in ways that create sugars like glucose, as well as oxygen gas. But many of the reactions that happen, we're talking about something that might be solid and may not be able to move around. And the way it can most easily move around is if it dissolves in something like water. So most reactions that you're going to encounter occur in some sort of solution. In lab, they often happen in water, although there are other liquid solvents that might get used, especially once you get to organic chemistry. In this video, as I said before, we're going to be talking about aqueous solutions, which are solutions in which the solvent is water. So let's talk about two solutions you may be familiar with, lemonade and maple syrup. Now, both of these have sugar in them, and so I want you to think about which one has more sugar. I pick these particular solutions because this is something that you have a built-in sensor for, so you can do this experiment at home without any specialized equipment. And our specialized sensor, of course, is our tongue. So imagine taking a big gulp of lemonade. You can imagine that it is sweet. Now imagine taking a similar gulp of maple syrup. Which is going to be sweeter? Odds are pretty good. It's the maple syrup. Just because these are both aqueous solutions that contain sugar does not mean that they have the same concentration of sugar. So let's talk about what concentration means. One way you can think about this is on a large macro scale. So here is an example of a very concentrated situation. We have a whole bunch of clowns in what appears to be a Honda Civic. And the question is, how many clowns are in this Honda Civic? Now, I actually went through and tried to count and estimate, and best I could figure was that if there's clowns in the trunk, there might be 20 or so. So let's just say it's 20 clowns in a Honda Civic. Now, imagine what would happen if those clowns got out of the Honda Civic and they got onto a tour bus. Suddenly, they're not so concentrated anymore. So this is an example that I'm going to come back to in the next video. Just keep it in mind. But basically, when the clowns are in the Honda Civic, they're right up next to each other. And the ways that they interact are going to be very different than when they're on the tour bus and they have more space between them. And basically, someone's elbow is not in someone else's face. They interact very, very differently. And actually, they even interact a little bit less because they're farther apart. So concentration makes a big difference in terms of what sort of chemistry can happen. If you want a definition of concentration, here this is going to be a mathematical definition, and it's going to be a ratio. And it's going to be how much stuff is dissolved. In other words, how much solute do you have divided by how much stuff it's dissolved in, how much solvent is present. And there are many, many ways by which you can calculate concentration. There are many ways you can express how much solute you have. There are many ways you can express how much solvent you have. And we will talk about a number of different concentration units over the course of this class. But for today, we're going to talk about one specific sort of concentration unit, one that gets used probably more than any other in chemistry. So before we get too mathematical, I will say there are a couple of terms that we use a lot. One is dilute, which means compared to how much solvent you have relatively little solute. And then we have concentrated, which means you have a large solute to solvent ratio, however you measure that ratio. So if you think about the concentration of sugar in the two solutions we were talking about earlier, if you want to make lemonade from lemons rather than from a mix, you might use a cup of sugar to 1 quart of water. Whereas with maple syrup, now, I mean, obviously if you're buying real maple syrup, you don't make maple syrup, but if you're poor and you have to make fake maple syrup, which is what happened when I grew up, you basically put 1 cup of sugar in a cup of water and then add your maple flavoring. So in both cases, we are looking at how much solute we have, and you'll notice that we have the same amount of solute. We have 1 cup of sugar in each of these solutions, and then we have how much solvent, and this is why the concentrations are different. For the lemonade, we have 1 quart of water, which is basically 4 cups, whereas with the syrup, we only have 1 cup of water. So we have the same amount of solute, but in different amounts of solvent. Now in chemistry, we use this unit called molarity. And the unit of molarity is a calculated unit. Basically, it's moles per liter. So essentially, we're talking about how much solute we have in moles divided by how much solvent we have in liters. So if we, for example, put 5 grams of salt, by salt I mean sodium chloride, and we dissolve that in 250 mils of water, which, by the way, this is basically a teaspoon of salt in a cup of water. So what's the molarity of that solution? So remember that molarity starts with moles on the top of the ratio, so we need to figure out how many moles of solute we have. The problem does not give us a number of moles, but it does give us a mass and a molar mass. So we can calculate the number of moles. So basically, we're going to take our 5 grams of salt and we're going to use the molar mass as a conversion factor to convert that to moles, and we're going to get 0.08556 moles. Again, that's not the correct number of sig figs, but I don't round to the correct number of sig figs until the end. The next thing we need for molarity is we need a volume. Well, we are given a volume right here, but it's not given in liters, so we need to convert it. 250 milliliters, and here we use the equivalence of 1 liter is 1,000 milliliters to convert that amount to liters, and so that's 0.2500 liters. Now, our molarity then is going to be the number of moles of solute divided by the number of liters, and this gives us this number, which of course has too many sig figs. We only have 2 sig figs from our 5.0 grams of salt. So we're going to report it as 0.34 molar. That's what that capital M means. And just remember, because we're going to be using this a lot as a conversion factor, that this capital M here really means moles per liter. So we can think of this as 0.34 molar. That's how we would say it when we're talking in lab. But when you're calculating, you need to remember that is 0.34 moles per liter. Another calculation we often do in regards to molarity is to calculate the number of moles we have in a solution. What we're going to do, we're going to take the fact that we have molarity equaling to the number of moles of solute you have, divided by the volume you have. So basically what we're going to do is multiply both sides by volume, and that will give us this equation. The number of moles of solute is going to be the molarity of the solution times the volume. How many moles of sodium chloride would we have in 100 mils of a 0.2 molar solution? We're going to use this equation. One thing you need to remember is that molarity is moles per liter, and your volume therefore must always be written in liters when you use this equation. So we're going to take this, we're going to turn that into 0.1 liters. If you don't know how to do that conversion quickly in your head, make sure you write it out with a conversion factor until you become comfortable with it. So our number of moles of sodium chloride is going to be 0.1 liters times 0.200 moles per liter. And you can see how the liters here are going to cancel out and leave us with units of 0.0200 moles. Now, here's a different problem, and I basically want to know how many moles of sodium chloride are there in 200 mils of 0.200 molar solution. Now, once again, we're going to take this and we're going to turn it into liters. You can see that the number of moles we have is 0.20 liters times 0.200 moles per liter, and that's going to be 0.04 moles. Now, what I want you to do is to look at these two problems. We have the same molarity in each problem, but what you see here as the difference is that one of them has twice as much volume as the other. So we have the same molarity, we have 2 times the volume, and we end up with 2 times the moles. Let's go back. I put the first problem back up on this slide, but now what I want you to look at is how many moles of sodium chloride are in 100 milliliters of a 0.4 molar solution. So once again, we're going to multiply the number of liters times our molarity, and we get 0.04 moles. So once again, I want you to notice that we have the same volume, but we also have twice the molarity. So in this case, we have the same volume, but we have twice the molarity, so we have twice the number of moles. It really helps you as you do these problems to understand how changes in volume and changes in molarity relate to the number of moles you have in a system. All right, now we're going to talk about how to make a solution of known molarity, because doing the sorts of problems that we did previously in this video are not very helpful when it comes time to get into lab. So if you're working, for example, as a lab aide and your SIT asks you to make 1 liter of a 0.1 molar calcium chloride solution, how would you do that? So anytime you have one of these problems, you're going to start by calculating the number of moles of solute that you need to make your solution. You're going to use that to calculate how many grams of solute you use. And then what you're going to do is you're going to take a volumetric flask that's half full of water, measure out the mass of solute that you calculated, and you're going to dump that into the solution. You're going to cap the volumetric flask. You're going to shake it up until it's dissolved, and then you're going to fill the volumetric flask with water to the line. Now, there are some people who think that you should just fill it all the way to the top and then add your solute, but that doesn't really work, because usually what ends up happening is your solute actually takes up volume as well, and you'll end up with slightly more solution than you anticipated. All right, let's try a problem. How would you make 500 mils of a 0.30 molar solution of sodium chloride? So again, we're going to start by calculating the number of moles of solute that we need. We know that we need 0.500 liters of a 0.30 molar solution. So we're going to calculate the number of moles as just being molarity times volume, and that gives us 0.150 moles that we need to add to our solution. The next thing we need to do is we need to calculate the number of grams of solute. So if we have 0.150 moles of sodium chloride, what is that in terms of grams? Here we're going to use the molar mass of sodium chloride as a conversion factor, and that will give us 8.766 grams. So now we're going to get our volumetric flask, put some water in it, and then we will weigh out 8.766 grams of sodium chloride and dump it in. We're going to shake it up so it all dissolves, and then we're going to fill our volumetric flask with water up to the line, and that's how we'll do it. When it comes to a laboratory situation, the number one way that we measure how many moles are in a given amount of solution is by using molarity. There are situations in which we don't use molarity, and we will talk about those in Chem 2. But for now, you just need to know that molarity is the primary way we calculate concentration. I hope this was helpful, and I look forward to seeing you again soon.